Hey everyone, this is Will from therandomcoder.com, and what we're looking at here is an implementation of the A* search algorithm, which is a pathfinding algorithm that builds upon Dijkstra's algorithm. Specifically, it adds a heuristic value that guides the search generally towards a goal. So I originally wrote a version of this using Visual Basic for applications of all crazy things, Excel, in fact. And yeah, it produced this cool looking output here, and I thought it was cool then. I still think it's pretty cool. So yeah, I decided to port it over to a TypeScript project using some more modern technology such as HTML canvas. And yeah, I thought it was a great idea for a video. And yeah, so that's what we're going to be going over in this video. We're going to go through creating the TypeScript project itself, creating the UI, and implementing the algorithm. So I hope you enjoy the content, and yeah, any questions or comments or feedback you have, please do get in touch. I'm really interested in sharing my experience to help as many people as possible. So any requests you have, very, very helpful. So with that, let's get started. So the first thing we need to do is set up our TypeScript project. We'll call it Pathfinder, and I'll just create a git bash terminal here because we're going to need to execute some commands. And if we go to the TypeScript homepage, you can click on download. And if you scroll down, there's this section for bootstrapping a TS project. And here are instructions for creating a new project in whatever kind of web framework or environment that you're working with. So we only want something very simple. So I'm going to go with this Webpack option here. So if we click on that, it takes us to the Webpack page. And we've got a section for TypeScript. So it says here that this guide stems from the Getting Started guide, and you can follow the whole thing if you like, but the only thing we really need is the install, which gives us the Webpack and Webpack CLI. So I'm going to run that now on this git bash terminal. And if I flip back to here, we've got some additional instructions for setting up Webpack for TypeScript. So we've got the TypeScript, obviously, and TS Loader, which is just a little module that tells Webpack how to handle TypeScript files. So there's one more thing that we need. If I just run npm I -d, it's the HTML Webpack plugin. So that just tells Webpack how to handle HTML documents. So then what do we want to do next? There's a bit more configuration we need to do. So if I just open a VS Code instance here and just make that a bit bigger. If we follow the instructions on this Webpack page, we need a tsconfig file, which we can easily create, tsconfig.json, and paste that in. And we need a webpack config.js, which we can just create here again, webpack.config.js. Just going to zoom in a bit so you can see better. And there's one more thing that we need. In fact, I haven't copied the whole thing there. There's this. Yeah, there's one more thing that we need, which is to configure the HTML plugin that we just installed. So HTML Webpack plugin equals require HTML Webpack plugin. Okay, and we need to just add that to the array of plugins. And we go new HTML Webpack plugin, and we give it a title, which I think can be anything. Call it HTML plugin, and template needs to be the file that we're going to be using as the HTML template. So let's create a new folder called source. We'll create a new file called index.ts, which will be our TypeScript entry point. We'll create a new file called index.htm. And in the TypeScript one, we can do console.log hello from TypeScript, exclamation mark. And in here, I think I can just copy paste a basic HTML document, nothing special, title, bit of styling, a heading, a canvas, which is important. We're going to be using that for the animation that we're going to be creating later, and just a small section at the end for some output for the user. So final thing we need to do is just set up a build script, Webpack build. Now I think everything should now be in place for running npm run build. And what this will now do is use Webpack and the configurations that we've just created to produce an output directory that contains some bundled code and an HTML document according to the plugin that we've added. So you see dist has been created. It hasn't pulled in the correct stuff yet for some reason. Oh, I haven't saved this file, so that's the reason for that. The other thing I've just noticed is we've got this thing moaning about a mode option not being set, which we can easily suppress by setting the mode to production. So we can do that and run the npm run build command again. Okay, so that has built. This now contains all of the code from the HTML file that we created, and it's referring to the bundle. So now the only thing left to do is to serve the content. So this dist folder is ready to be deployed to production somewhere. So if you have Versal, for example, you can pretty much drag and drop this entire folder into Versal, and it will deploy the code and serve it up. So on a local environment, we can use a module such as serve. In fact, it's npx serve, and that should serve up the files for us to have a look at them. Copy that and paste this over here. And there we go. We can see that this is now showing the content of that directory, serving it up to the user. And if we right click and inspect, we get hello from TypeScript. So our TypeScript code is being loaded nicely as well. So at this point, we're ready to begin. So there's another way that we can serve up the content on a development environment, which is a bit more convenient when we're making alterations to the code regularly. And it employs something called hot reloading, and it will essentially listen out for changes to files and reload the output so that we don't have to keep regenerating the code all the time manually. So I'm going to create a script here called dev, and I'm going to call, so the command is Webpack Serve. So it's built into Webpack, and we can now use Webpack Serve by executing npm run dev. And you'll need to install the Webpack dev server. And now that that's running, we can scroll up and get the output path and load it up. Yeah, that's changed from localhost. Localhost is fine as well. And yeah, we can see that this is now being served using Webpack Serve. Now the benefit to doing this is if I were to go in here and make a change to this file, observe this output here, reloaded. When I save that, you can see that it's actually reloading all of the content, and we now get the updated TypeScript code executing here. So this is going to be really handy when we're working on our project to get the updated version displaying when we're working. One of the first things that we're going to need is a way to capture the details of the maze that we're working with. So we're going to want like a maze definition that contains where the paths are, where the walls are. So I think a convenient way for us to edit that in code is to use an array of strings, where each string has a character that represents a path or a wall. And if we have that shown in lines in the code, then we can easily edit it, and it maps directly in terms of its appearance to the output that we're going to expect on the screen. So let's create something like that. And perhaps we'll have the hash character to represent a wall and a space character to represent a path. So I'm going to create a maze data array. And having this represented in this way is very convenient for the reason I said. We can now edit it to add some intricacies to the maze. But this is going to be a bit awkward to work with when kind of trying to reference cells. So I think what would be useful is to translate this data into something more easy to interrogate. So like a two-dimensional array where each item in the array represents a cell. So let's first create an interface for the cell, and it will have an X and a Y, and whether or not it's a wall. And now I think we can use that interface to write some code that maps the strings to that interface, and then we have a nice two-dimensional array that we can work with. So let's have a look. So here, the row index is essentially going to be the Y coordinate, because as we go through each row, it's going in the Y direction. Now we can split on an empty string here to convert the characters into an array of characters. Cell index. So as we're iterating over the characters in the string, that is of course iterating over in the X direction. So this cell index will be the X coordinate. So I think what we can now do, we just return this object, and we'll have the X coordinate, which will be the cell index. We now have the Y coordinate, which will be the row index. And now we need to know whether it was a wall or not. So if the character, which is the cell, equals the hash character, then, well, we don't even need a ternary. So if it's equal to this character, then the result of this expression will be true. And if it is not this character, then this will be false. So therefore, this wall character property will be set to the correct Boolean value. So this now should contain a two-dimensional array of what we need. Okay, so now it'd be great if we can represent this grid of data in the canvas that we have. So let's first of all get the canvas element, document.get element ID. And if we look here, we know the ID is canvas, so we can get it by the canvas ID. And let's calculate a width and height. So we're going to set the canvas.width to be equal to, well, it needs to grow or shrink based on the number of items that we have. So let's do maze dot, well, we'll use the first item, the number of items in the first row, to indicate the size, and we're going to multiply that by some value that represents the size of the cells. Let's go with 50 initially. Maze.length times 50. We're going to probably use this 50 more than once, so let's just set it in a constant Now, TypeScript is complaining about these width and height properties because it doesn't know what this type of element is, but we can tell TypeScript that it is a HTML canvas element, and that will now suppress the warnings. So we'll save that. The next thing to do is we want to draw a rectangle for each of the cells. So we've mapped this data to a two-dimensional array of cells, and we now want to iterate over everything, and based on the X and Y coordinates and whether or not it's a wall, we want to either display a rectangle that is a wall or a rectangle that represents a traversable path. So let's iterate over all of the cells. There's a handy way of doing that actually in a two-dimensional array called flat. I don't know if you've ever used it before. But what that does is it takes an array of arrays potentially, at any kind of level of nesting, and it translates that. Essentially, it spreads all of those arrays into a single long array. So that's kind of convenient here because we can now just iterate over this once with a for each rather than having nested for eaches. And we will have a cell, and for each cell we will want to do canvas dot fill style. There's a step I missed. Whoops. So in order to actually display graphics, we need to use the context, which I think is the device context. Here we need to do context.fill style, and we will set that to cell.wall. So if it's a wall, then we're going to set it to red. Otherwise, let's set it to white. So that's cool. Now let's draw each rectangle. So context.fill rect. And we need an X coordinate, which is handy because cell.x. And we need a Y coordinate, cell.y. And we need a cell size to represent the width and height. We've got a problem here though, because these are index values rather than pixel values. So in order to translate that into pixel values, we will need to multiply by the cell size. And if we save that, we get this, which is looking pretty good. Now, I personally quite like the style of having a gap between each of the cells. So to achieve that, we can just do +1, +1 there. And that shifts each of the rectangles by +1. So each are now overlapping by 1 pixel. So we need to actually shrink the width by 2 pixels to then get a gap on the right hand side of 1 pixel. And there we go. That looks pretty cool. I think at this point we can tidy up the code a little bit to make some smaller files that have a more dedicated purpose. So this maze data, for example, I think that especially once it becomes something larger, is going to be a bit awkward in this file. So let's create a dedicated file for that. And then here we can simply, import maze data. So we don't need this console log anymore. And I wonder whether we ought to put some of the maze manipulation stuff, the stuff related to the grid and the drawing of the grid, into a separate file. So let's create grid.ts. And actually, I'm going to migrate this over to grid.ts. I'm going to do the mapping in grid.ts. I'm going to do the canvas setup in grid.ts. In fact, I'm probably going to do most of the stuff in grid.ts. This cell, I guess makes sense to be in here. And I think perhaps it probably will be useful to be able to draw a set of cells in a particular color, things like drawing the path and for drawing other nodes of different colors, like visited nodes. That's going to be a subset of the main array of grid cells, and we're going to want to paint them in a different color. So if we had a dedicated function for that, that would probably be quite useful. So I'm going to take this maze and I'm going to export the maze and save that. Then I'm going to import it here. Import from grid. And I think what I will do is create a const for walls and a const for paths. Maze.flat, and do a filter if the wall, I'm going to destructure the wall property and say if it's a wall, then we'll keep it. And for paths, we'll just invert it and say if it's not a wall, we'll keep it. So now the walls and the paths variables contain a list of cells that are walls and paths, respectively. So now, if we had a function called paint cells, we could then pass in, sorry, my bad, cells, which is a cell array. We could then do this on the cells. Let's move this into the grid function and export paint cells as a function. And I quite like the idea of separating out the fill style into an explicit argument, which means we can then control the color of the various things rather than putting that logic within this function. So we'll take that out, and in index, we can then, I don't need this anymore really because I can remember the colors. I can then call paint cells and pass in the walls and color, which for the walls will be red, and then do the same thing for the paths. And I think, in theory, that should work. Let's see what happens if we change the color of the walls. Fill style. Yeah, I'm not updating the fill style. There we go. Just needed to refresh for some reason. Yeah, there we go. That's working. Save. So for some reason it just lost the hot reloading. So yeah, that's now working. And that's the original style. So yeah, I think that is a lot tidier than it was before. Right, now let's implement a very simplistic version of a pathfinding algorithm. So it's not going to be the full one yet, but we'll create a function pathfind equals new function, and we'll give it a start node and an end node. We'll give these the type of cell, which is currently not exported from here where we define the interface. So we'll export the cell and import the cell here. Okay. And inside this pathfinding algorithm, we're going to want to do a bunch of things. So the first thing is to create what's called a fringe. So the fringe is essentially the boundary between the explored territory and the unexplored territory. So it's an array of nodes that represents the possible things that we could explore next. So yeah, you're going to have some explored territory, and there's going to be a boundary between what we know and what we don't know. So that is the fringe. And to begin with, we could actually put the start node in here straight away, because we're always going to start with a single node in the fringe, because that's the one thing that we know at the beginning. So next, we're going to want a loop, which is going to progressively explore where we can go. Okay, so we're going to keep exploring the fringe and processing items from the fringe while there are items that exist. And I always like to put in like a safety mechanism here, so that if for some reason our code, there's like a bug or something and the length just kind of spirals out of control, we've got a way that we're not stuck in a tight loop that keeps processing for infinity. So yeah. So what we'll do next is we will get a node from the fringe. We'll do, I'm going to set a let this node just to create the variable, and we'll reuse it in this loop. We'll do this node equals fringe dot pop. So we'll get an item from the fringe. In fact, I want to use shift to always take items from the start of the array, because we want to preserve a strict order in the fringe so that we process the items that are of most interest to explore first. And next, what do we need to do? So we need to explore where you can go from the current node. So another common concept in AI is to have a successor function. So what that means is, given a particular node, what are the potential successor nodes that you could end up at by taking some move from the current node? So for that, we need a successors function. So there are 4 potential places you can go from a particular node or cell. So if you take this node here, you can go up, down, left, or right. So let's capture that here. So now we have an array of objects that represent the deflection that you can move in the both X and Y directions. So you can move up by -1 Y, you can move down, you can move left by -1 X, and you can move right by +1 X. So we can now use this array of adjacent objects to calculate the position of the item or node that we want for the successor nodes. So here we want to get the node from the grid or the maze that is calculated by the adjacent deflection. So we probably need a function for getting a node, which I'll write now. Okay, so this will get the node at a particular position. However, there's something we need to be careful of here, because we are just yeah, if I put this where it's going to be used, get node. Okay, so now I'm calculating the successor nodes from the current node. So I added that here. So given a current node, we want to get the node at the position of the current node X plus the adjacent node X. So you can see that this is going to iterate over these 4 items and calculate the X and Y coordinate for the up, down, left and right positions. So yeah, that should get back to us the nodes that we can potentially move to for a given current node. We have to be a bit careful because of this -1 and +1. We can end up moving off the edge of the grid. So let's add some code to just protect against that. So in the case that we're out of bounds, we're just going to return null, and then we can filter out nulls in the calling function here, yeah, when we map. So we call this, we have a map, then let's do another map to say node is not equal to null. Sorry, that should be filter. Filter out the nodes that are not equal to null. And now finally, we can only travel to paths and not walls. So here we can't travel up and left, we can only travel right and down. So we need to add another check to take account of that. Let's just destructure the wall property from the node, and if it is a wall, yeah, we only want to keep it if it's not a wall. My bad. Yeah, so we only want to keep the successor node if the adjacent thing is not a wall. And that's looking pretty good, I think. Let's return the successor nodes. Okay, so now we're in a position where we can use the successors function to retrieve the next steps for a given node. So we can do const successor nodes equals successors and pass in this node, and we'll get back the list of potential places you can go from that node. And what we can do then is pretty much just iterate over the successor nodes and add them to the fringe. Let's just go with that and do fringe push, and we'll push each successor node onto the fringe. So this is just going to keep searching forever. So we need a way to detect have we reached our goal. So something else that would be useful, in fact we probably want it here, is a have we reached the goal check. So if, and I'm going to create a function here, is same location. So if this node is the same location as the goal node, then we're going to do something else here. In fact, let's return, let's just return with a string that says found path. Found path, that'll do. So we need to create a function for this. Const is same location equals a new function, which will take a source as a cell and a target as a cell, and we'll just check. Well, we can probably just return. Yeah, return source.x equals target.x and source.y equals target.y. So if the source is x and the target, if the source x and y both equal the target x and y, then it's the same location. Okay, let's change that to goal node. Sorry, end node. Okay. Pathfind. Now, I wonder what's going to happen if we call this now with a start node. Let's say it's x is 1, y is 1. I think we need a wall. That's false. And not that it's using the wall. Let's call that, I don't know, let's go explicit. That's 1, 2, 3, 4, 5, 6, 7, 8, 9. 2, 3, 4. So 9 and 4. Save that. And what do we get? So let's just do const result equals that. And why don't we use our output section on this HTML document to output the result? So we can do output equals get document dot get element by ID called output dot set inner. Is it inner? Yeah, inner text equals the result. Save that, and hopefully we'll get some output that indicates that it's running forever, I think. Yeah, so yeah, I see. So let's have something here that does return path not found there. So if it escapes, then we get something that tells us. Yeah, so by reducing this check here, I can see that it's coming up with path not found. And the reason is because we've got nothing that stops this from just going round in a circle. So it's just processing the same thing over and over again. So how about we add a explored array? So we can say const explored equals an empty array, and when we take something from the fringe, we can mark it as explored. Yeah, so we go here and say mark as explored, do explored.push this node. In fact, I'm going to just destructure that into a new object just so that it's a brand new thing separate from the original. Not that I think we really need to do that. And then so we only want to add new things to the fringe if they haven't previously been explored. So if let's go explored.sum equal the node is same location, if the successor node is the same location as one of the explored nodes, then let me just say that's a cell array. Then what do we want to do? We want to return. Yeah, so if we've been there before, then return, and if we haven't, then we'll add it to the fringe. Okay, so I just found a little bug in what I'd written so far. So I got these coordinates round the wrong way. So of course the first argument, or the first array, is the row, and the second is the column. So yeah, so just fix that. And now we're getting path not found, so that's fine. So to help with understanding what's happening, I think I'd like to see what exactly is going on with the fringe. So I'm going to change where we paint our cells. So rather than doing it once, I'm going to put this within our loop. Get rid of this log that I was using to debug the problem we had a minute ago. And I'm also going to add one here for the fringe. And let's make it a new color. And save that. So hopefully, okay. So that's interesting. It got to here. What we didn't see is any animation. Now, I think the reason for that is you need to allow, because JavaScript is single threaded, there needs to be like an escape for it to be able to do things like updating, painting, and things like that. So there's a bit of code that we can add to allow that to happen. That is this. So if I make this async and await this promise. Oh, we need to fix the type now, don't we? So that will be a promise of type string. And this we need to await, which we can't do because it's a top level function. But we can do then and do results function. So put this inside here and save that. There we go. Excellent. Cool. So that actually did a bit of a little animation there, which is pretty cool. So if I now just make the color a bit more obvious, that's awesome. So we just saw that it's explored and stopped here. That's because I reduced the fringe to something too small. Let's now make it bigger and see if it reaches the goal. Awesome. And we found a path. I think we can further enhance the animation by plotting the explored nodes as well. We'll make them blue. Save. And that's kind of awesome. Now let's tweak some of these colors to make it look a bit nicer. So we'll make walls black. We'll make the default path color like a blue. Let's make an explored path green. And let's represent the fringe with like a bright yellowish color. So that will match. Yeah. That looks pretty nice. And one other thing that I think would be good is to show the route to the current cell that is, or the current node that's being explored. So we want a way to trace back to the original start. So from each node, it needs to know the route that it took to get to where it is. So we've got this successors function here that rather conveniently constructs the nodes for us. And what we could do is have some kind of a hierarchy that is kept on each individual node that represents the path. So what we can do is add a previous item. So I'm thinking, so we've got this cell here as the return type, but I'm thinking we're going to need a new interface to represent a node. So let's do interface node extends cell, and let's say previous, and give that the type of node. So now I'm going to make it optional. So now we can have a node that has a previous node. So when we create our successors, let's do a map. So for each successor, well, first let's change this to node, and let's say that the successor will return an object, which is the successor node. Oh, the successor node, but also will contain the previous node, which will be the current node. So now, each time we create a successor, it will keep track of the node that came before it. So we should be able to use that to get back to the start again. But we can go const get path. So for a given path, sorry, for a given node, yeah, so for a given node, we will return the node.previous. So we'll do a ternary here. So if we have a previous node, then we're going to return the current node in an array plus the previous node, yeah, the get node of the previous node. Otherwise, if there are no previous nodes, we will just return an array that contains the current node. Oh, I do apologize, get path. So yeah, we're going to essentially recurse. Okay, and we're going to return a node array, and this is a node. So get path, yeah, is essentially a recursive function that traces all the way back to the previous, the as early node as possible. Otherwise, yeah, it will return the current node. So that will recursively get the path. So we could add another paint cells function here and do get path this node and specify a new color. Let's call it, let's make it red. And see what we get. Right, now that looks cool. So you see how it was jumping around all over the place? That's because it's not a very efficient algorithm at the moment. It's pretty much a brute force algorithm. Yeah, that's why it's sort of hopping around all over the place rather than making a more efficient route to the path, to the goal. But it's kind of awesome to see that we have found a path, and now we can output some interesting information as well, such as the length. Let's go here and go const, I don't know, found path equals this of length, found path.length. So now when it gets to the end, it's going to output the length of the path that we found. Length 18, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So that is correct, which of course it would be. So yeah, that's pretty good. But we need to make the algorithm now more efficient because this is brute force, a very simplistic algorithm. So now we need to implement the A star kind of heuristics in this function. If we watch carefully, you can see that then, for example, if I just run this again, it's processing the route to the fringe multiple times. But we've got this here where we're doing a check so that we don't process the same item multiple times. So we've got this thing where we're keeping track of the explored items. But this is places where we've actually fully processed the node, and the fringe, as I've explained before, is the boundary between what we have explored and what we haven't explored. So this is kind of escaping that check, and something we can do to fix that and make this a bit more efficient is to just create a new array of the explored items, but also include in here the fringe. So when we get our array of successor nodes, we only want to push them into the fringe if they are neither explored or they don't exist already in the fringe. So let's see what that gives us. Yeah, and you can see that was way more efficient, much faster. So what I'm going to do now is I'm going to paste in a much bigger maze. It's in fact the maze that you saw at the beginning. Huge. It's randomly generated, but there is a path from the start to the end node. And I'm going to save that and see what we get. So that's kind of cool. In fact, I'm going to move this over now so that you can see it better. The cells are a bit big. We can make that smaller, but this is a bit weird. So it's gone to this path all the way down here, and then it stopped. And it stopped because it's actually found the final goal node. If you remember, we explicitly hard-coded them. So something like over here. And it's found that node. But then why isn't it showing the route to that node? That's a good question. And the answer is we're painting the cells here, but we're not painting the cells again when we find the node. So the route that we're showing here is actually one iteration old. So we need to do this again, which means it's probably a good idea to create a function here to capture all this in one place. So let's do that. Good. So now let's just refresh this. So cool, that's still working. But now what we can do is we can copy this and paste it here. So when we found the result, well, we can put the found path here. And hopefully, yeah, there we go. So it's gone all the way down here, found the path, and gone up here. So that's pretty cool. That's working. Now let's see if we can make the grid a bit more of a sensible size so that we can see what's going on in this newer version. So we will go up here. Where is it? Grid. Yeah, we'll make the cell size 15 and save that. And hopefully, yeah, that kind of fits. Yeah, in fact, that perfectly fits up to the edge. Oh, I've just noticed this is a modified version of the same maze, actually, with a little shortcut that I was playing around with. But we can use this. But it's stopping there when, in fact, we want the goal to be down here. As another point, we probably want to show the start and the end when we output the scene. So when we have, maybe in the path, whenever we call this paint scene, so if we found the full path, that's fine. But if we haven't found the full path, it's a partial path, but we also want to show the goal node. So hopefully that'll just be a bit clearer where the goal is. Yeah, so you see briefly it shows the red dot there. So now we can update the destination node, and let's be a bit more intelligent about this x coordinate. So it's going to be the maze, the first element of the maze, dot length -2, I believe, because we've added 1 and we need to -1 anyway. So let's do the same with y. With this, of course, we get rid of the second part there. Good, let's save that. And now we're getting somewhere. Now you may notice a subtle difference between this implementation. So here, this actually is quite helpful because it clearly shows that we're, yeah, so these yellow ones are the fringe, but it's exploring, there are no unexplored paths around here, for example. It's exhausted everything to the furthest extent possible. So it isn't, it's not the A* search algorithm quite yet, because it's not being guided by a heuristic value. So once we give it a heuristic value, and I guess some understanding of the cost to travel to a particular node, only then is it able to be a bit more efficient in this exploration. There's a way I can show this really, really clearly, actually. So if I take the maze from here, maze data, and I'm just going to temporarily zoom out to create a blank row. So what we have now is an empty maze. So this should be really easy to get from A to B. But as you'll see with this algorithm, it's still exhaustively searching the entire maze, which is wasteful because it doesn't need to do that. It can just kind of, like, all of these fringe nodes are equally viable candidates for the next node, and you could just pursue one in like a depth first search kind of way. So let's see what we can do to achieve that. So in order to make it more efficient, we need to keep track of some additional things for each node. So the first is a cost. So what was the total cost that it took for us to reach that node? And the other is a calculated heuristic value. So that will represent a kind of best guess as to the amount of cost that it's likely to take from that node to get to the goal. So let's implement that. So here where we have the previous, so let's add on to here a total cost. We'll make that optional, and we will set it to a number. And we also want the heuristic, which is also going to be a number. Good, and that can also be optional. So now when we populate the successors, we're going to now calculate these values. So whenever we get to a new node, we're going to say that the total cost is equal to the current cost. Yeah, it will equal the, let's say, either the current cost, because it's optional, it will either be the current node dot total cost, or if that's not populated, just the number 0 plus 1. So we need to change this to be a node, and that is now good. And we can add a heuristic value, which will equal, well, there's different ways of calculating a heuristic value. Popular ones in Pathfinding are calculating the distance, as in the hypotenuse between, like, if you imagine a triangle, or something called the Manhattan distance. So the Manhattan distance is as if it particularly applies to like a grid, and it's essentially the number of squares that it would take if you traveled like in American style, like blocks, yeah, when you're navigating streets. So the Manhattan distance is calculated by summing the deflection in the x and the y axis, and I think we'll go with that. So heuristic Manhattan, and we will pass in the node and the goal node, which we don't currently have. Goal node, which is a node, and that should be current node as well. Successors, right, so here we need to pass in the goal node. Good. And now we just need to implement this heuristic function. And I think it will be equal to, well, we have to have the source node. Well, let's just go with source node and target node. And it will be the difference between, if we take the absolute number, because it will either be positive or negative, the current node, sorry, the source dot x minus the target dot x. So whichever way round x and the source and the target are, it will calculate the deflection as a positive number plus math.abs of the source.y minus the target.y. And that will give us the heuristic value. So that's awesome, but we're currently not using them. So we need to ensure that when we add them to the fringe, now I mentioned before about the fringe being ordered, and we want to choose the node from the fringe that is the best node to explore next. So what we can do here is, once we get back the successor nodes, when we insert them into the fringe, if we insert them in a way that preserves the order of preference that we want to process them in, then that should make for a pretty efficient algorithm. So let's do it. What we can do here then is process the successors and insert them in order. So we can do for let I equals 0, I is less than fringe dot length. So we're going to iterate over the fringe here, plus, and we're going to figure out where we need to insert it. So we need a function to decide which nodes are better than other nodes. So let's just write the code and then we can implement the function. So if is node better the successor node than the currently processing fringe node, then what are we going to do? We want to insert the item at that position in the fringe. So we can do fringe.splice at position I with a delete count of 0, but we want to insert the successor function, the successor node. So we know that this node is better. So if it happens to be on the first iteration, let me just save that to bracket. Yeah, sorry. So yeah, if the node on the first iteration happens to be better, then it's going to be inserted right at the very beginning, because I is going to be 0. So it's going to be inserted at that position. And it's going to just iterate over the fringe until this is true. So when the successor is better than the fringe item, at which point it's going to insert it at that position. Now we don't want to push it again, so here we will need to return. And now we just need to implement the function for deciding if a node is better. Let's put that there. Const is node is better. And we're going to want pretty much the same as this, actually, although it will be a node. And the way to decide if a node is better will be as follows. So we need to take account of the cost that it took to get to that node and the heuristic value. And I mean, this is at the core of what it means to produce an A* search algorithm. So we're taking the cost, which is the source dot total cost plus the source dot heuristic value. So if the source cost plus the heuristic cost is less than the target cost plus the heuristic cost, then I think it's fair to say that the node is better. So let's see how that looks. Okay. So it's still pretty inefficient. And I think the reason could be because we've got nothing distinguishing between all of these equally weighted nodes. So they all have an equal cost plus heuristic value. So we need a way of kind of deterministically ordering them. How can we do that? So one thing we can do is to have like a tie break situation. So if these are equal, so rather than the node not being on the whole better, as in the cost plus the heuristic is a lesser value, you could have a tie break situation. So if, let's just write it. So, or if the total cost plus the heuristic is exactly equal to that, and the source dot heuristic value is less than the target dot heuristic value. So that means it's closer, essentially. In that case, yeah, we've got a particular preference towards, if you've got equally costly nodes that you can go to, you're going to have a preference towards ones with a lower heuristic value, which means it's nearer to the goal. So it's going to prefer to explore nodes that are nearer to the goal of an equal cost. And let's just flip back to here. Yeah, and that's executed. So wow, that's a lot faster. that's looking good. I'm not quite sure I fully understand why it's bumping up and down. But we'll go with it. So I'm now going to paste in the maze that we were using earlier, now that we know that it's pretty efficiently heading towards the exit. Let's see what we get. Now we're getting pretty darn close, I think, to the final version. Awesome. I think that's pretty much working. So one thing that I just want to do to make it look a bit more appealing, you see we've got a border between all of the cells. I just want that to be present only on the path. So we can add an argument here. You see where we do +1 and -2, that is where the border comes from. So we can do border size equals 1, let's say, or 0 actually. And we'll do plus border size, and we'll do 2 times border size. So that will get rid of the borders completely, which actually looks pretty good already. But I think I would prefer for the path to have a border around it. So yeah, there we go. Maybe the same with the fringe items as well, actually. Fringe. Yeah, now that's the same as before, the version that I showed at the beginning. Although we've got a pretty good version of this working already, it's still not the optimal solution. And in fact, it's in this specific example, it's not producing the shortest path quite yet. It's very close, but still not perfect. And the reason that this is happening is because when we get these successor nodes, we're filtering out items and not adding them to the fringe based on some quite naive logic, simply checking if it's the same location. So if you imagine traversing this path and it gets to this node, it will find the successors here, 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 and here. And suppose it found this cell for the first time and added it to the fringe, the cost associated with getting to this location includes some wasteful detour here. And there is actually a shorter path. But say when we're processing other routes, it finds that shorter path and attempts to add it to the fringe, it's going to be filtered out because it's a location that we've seen before. So what we actually need is a more intelligent check at this point, and we want to only filter things out if it's both the same location and it's worse than all of the other occurrences of that location that we've seen before. So we need a function for deciding if the location is a worse duplicate. So if the fringe item is a worse duplicate. So I'll just quickly write that. So the isWorseDuplicate function accepts a source and a target, similarly to the isSameLocation function that was there before, but it's also checking that it is a duplicate, that it is the same location, but we've also added in this extra check here to say if it's not a better node. Yeah, so if it's the same location and not a better node, then it's a worse duplicate. But if this check is true, then it will be not a worse duplicate and it will be kept. And so yeah, that means in the case where we process this cell, for example, we find this new successor node, which has a shorter path, then when it processes this is worse duplicate function, it's going to be the same location, but it will not be a worse node. So it will be a better node, and therefore this check will be false, and it will then add it to the fringe in the appropriate location. So if I now save this, hopefully, yeah, it now is able to find the optimal path. So just for full disclosure, while I was playing with the example a moment ago around the worse duplicate thing, I happened to discover a bug, and it explains this kind of bumpy structure that I was getting before that I was confused by. So the problem is that when calculating the successor nodes and processing them to calculate the heuristic value, previously, rather than passing in the successor node that I want to calculate the heuristic value for, I was passing in the current node, which is a bug. So if I correct that and have the successor being passed in there, it now looks a lot more sensible. So there we have it. It's done, and it's finding paths like a good pathfinding algorithm should. And I'm really interested to hear what any of you have to say about this. So I'm going to be keeping a good close eye on the comments. I will be responding to as many of you as I can. And any suggestions, thoughts, comments, requests for any content, or if there's any help that I can provide anyone, I'm here to serve in any capacity that I can. So let me know, and I will see you on the next video.